Okay, hi everybody. I'm going a little bit out of order today and talking about adiabatic expansions, 2E of Atkins, but I think this will work well. Way back in the day, several lectures ago, we talked about types of PV work: free expansion, constant external pressure, isothermal reversible, and there was a fourth one called an adiabatic expansion. That's what we're talking about today, adiabatic expansions. And I am going to cut right to the chase and tell you what an adiabatic expansion is. If you're taking notes, write this down and circle it. An adiabatic expansion is one in which no heat is exchanged between the system and surroundings. That is Q equals 0. On the exam, you will be asked to calculate some thermodynamic quantities, delta H, delta U, Q, for all of these different types of things. When you see adiabatic expansion, you can put Q equals 0. It's the gimme, okay? That sounds straightforward. The real trick here is in relating the variables, our state variables, during an adiabatic expansion. That is, I know that I start at some pressure, temperature, volume. What final pressure, temperature, volume will I be at? And before I get into it, it's worthwhile just to think about what our expectation is. Will the pressure, the final pressure, be lower in an adiabatic expansion compared to an isothermal expansion? And pause it for a second here and think about that. Will the pressure be greater than, less than, or equal to the final pressure in an isothermal expansion? I'll see you in a second. All right, welcome back. Here's the answer. In an isothermal expansion, the system is doing work. That's what I mean by expansion. That costs it energy. But isothermal expansions can maintain the same temperature by absorbing heat from the surroundings. It's doing work, but it's also absorbing heat, and those are exactly balanced, so there's no net energy loss. In an adiabatic expansion, it cannot absorb heat. So it's doing work, its energy is going down, temperature decreases, and pressure will decrease. Right? That's how you might think about it. Can we derive some math to help explain that? And as you might suspect, the answer is why, yes, of course. Let me switch some things. Let's do some calculus. Here's how you think about this. If I can get my pen to work. It was on, okay, I'm back in business. We're trying to relate state variables. The starting point for this is the first law of thermodynamics. du equals dq plus dw. In an adiabatic expansion, one of these goes to 0. It's this one. Right? That's what I mean by an adiabatic expansion. And now I think about du and dw. Well, before we talked about the constant volume heat capacity. That allows us to relate changes in internal energy U to changes in temperature. So du is equal to CV dt. And dw is minus pdv. We've seen that before. So I'm going to substitute these things in. CV dt equals minus pdv. Straightforward enough. What we have to remember now is that pressure is a function of volume and temperature, right? So I'm taking a derivative here with respect to volume, and over here with respect to temperature. Pressure depends on both of those variables. So I need to explicitly add that dependence in, which looks something like this. CV dt equals minus nr over vt dv. When you get expressions like this, I have variables on one side, and what I gotta do is put all my other variables on the other side. So here I'm taking a derivative with respect to temperature. I need to put all my temperature dependence on the left-hand side of the equation. And if I do that, I'm going to get something that looks like this. If I'm following my notes here, negative CV over NR dt over T equals dV over V. I can now integrate this. I can integrate both sides of this equation. So integrate, integrate. These, CV over NR, are all constants. This is essentially a dx over x. And remember that dx over x are natural log functions. So the integral of these two gives me the following. And I'm going to write this in a little bit different way here. CV over N is simply the molar heat capacity. So this is CVM over R, natural log TF over TI equals natural log VF over VI. Forgive my pen, it's jumpy, I don't know what to do. Remember, when I have natural log functions, I can take these leading exponents out here. They're not exponents, they're leading terms, and move them up here. So I can write this as TF over TI equals minus CVM over R equals natural log VF over VI. At this point, I have two natural log functions. So if I want to get rid of them, I will exponentiate both sides. Exponential. This gives me TF over TI to the CVM over R. I got a negative equals VF over VI. Last but not least, I want to solve this for TF. Okay, and if I do that, what I'm going to end up doing, I'm just looking at my notes here. Is raising both sides to the R over CVM power. That is TF equals TI to the VF over VI to the negative R over CVM. Don't do that. Last but not least, I want to get rid of this negative sign so I can flip these. And if I flip all of this, I end up with an expression that looks like this. And I wasn't sure how much space I would need. Ignore this. I wish I could get rid of this. Hang on one second. Let's see. There. All right. At the end of the day, here is the expression that I end up with. Again, if you're a person who likes derivations, you can go back and follow this, but these are the important expressions. TF over TI is equal to VI over VF, R over CVM. I haven't derived it here. I'll put it up on the worksheet problems, but if you want to calculate equations to relate pressure to volume changes, the expression looks like this: PF over PI. This is CP, the constant pressure heat capacity, over CVM. And unless you're really adept at this thermal stuff, these equations probably mean nothing to you, right? You'll get some practice on using them on the homework worksheet problems. But what I really want to go back to is that original question: are these final pressures in an adiabatic expansion less than an isothermal expansion? And that's what I'm showing you here, right? The blue line is a isothermal reversible expansion. The red line is an adiabatic expansion to the same volume. And what you can see, I'll just do it here, is that the pressure in an adiabatic expansion is lower than an isothermal expansion, just like we had predicted. So this all works, and we're good to go. In summary, An adiabatic expansion is one in which no heat is transferred. Q is 0. I'm getting all sorts of scam calls today, forgive me. The final pressure and temperature are lower in an adiabatic expansion compared to an isothermal expansion because no heat is exchanged. And we derived equations to relate these quantities. Check out the worksheet problems, and I will see you next time.